All right, hello everyone, and welcome to the SNAPP seminar. So I'm thrilled today to welcome Vianney Perchet for this seminar. So Vianney is a professor at the Centre de Recherche en Économie et Statistique and ENSAE since October 2019 in France, mainly focusing on the interplay between machine learning and game theory. His work is at the intersection of mathematics, computer science, and economics. And it ranges from pure theory, like the analysis of convergence rates for algorithms, to applications such as modeling user behavior and recommender systems. He's also a part-time distinguished researcher at the Criteo AI Lab in Paris. And today, his talk will be about improving profit inequalities, going beyond worst case, and analyzing the impact of weaker benchmarks. So without further ado, Vianney, the screen is yours. I'll be monitoring the chat, and if there are any questions, surface them to you.
Okay, thanks a lot for this. I need to share first for the introduction and for the nice for the invitation and the nice introduction. So we tried before. It should work if I'm doing this. Just checking. Is it working?
Yes, perfect.
Okay. So thank you for this invitation. It's it's a pleasure to be here with you on this online seminar. And as Ali said, I used to work on a lot on multi-bandit online learning, and I have discovered this field of profit inequalities and online matching, competitive analysis, and I like it a lot. And so what I wanted to do is at the end trying to merge those two fields, merging the ideas from online learning and the ideas of competitive analysis into a unified setting. And because I think it's really interesting, and this is the first my first attempt. Okay, there have been others, and we discuss about this. So during this talk, I will first present you some basic knowledge about profit inequalities, profit and secretary inequalities, and then I will present one or two papers depending on the time that I have, where we're trying to go, as it says here, beyond the worst case, the typical worst case analysis in those settings. And so yeah, I will mention my co-author in due time. Yes, I would like to say that if you have any question, feel free to interrupt. It's perfectly fine. If we don't have time to go to the both paper, it's perfect. I'd rather have many questions than many interrogation. Okay. So anyway, okay, so it's not working. Sorry. So before I start doing the introduction on profit and secretary, so let me just give you a very brief motivation and general setting. So this profit and secretary problem, the main question is doing online selection or optimal stopping, creating an optimal stopping rule where we want to take some decision under uncertainty. Okay, so what's going to happen is the following setting. We will at some point observe sequentially items, okay, of different value, x1, xn, and the point is to accept one of them, okay, and we will observe them sequentially, and each time we see one of those variable, we will accept it or reject it irrevocably. We cannot go back in time and change our mind. Okay, sometimes actually we have some papers where we can go back in time if we pay an extra cost, but here we just focus on the standard case where we cannot go back in time. So when you see x1, either you take it or you leave it. If you leave it, then you see x2, and then either you take it or not, and then x3, and so on and so forth. Okay, and the point would be to maximize the value of the items. Think of those variables as items that has value. So you want to maximize the value of the items that you picked. Okay, and I will define this my picking rule. I will call it tau, like a stopping time, and so x tau would be the value of the item I picked. Okay, and in this case, so we want to evaluate the quality of an algorithm, and to do that, we will compare ourselves against a prophet, which is someone that knows everything, that knows the whole sequence of values x1, xn. And so this prophet will obviously take, you also want to maximize the value of the item it picks, so you pick the best items. So the prophet will get the max of the xi. And what we want to do basically is trying to come up with some picking rule, decision rule that minimize that maximize, sorry, the ratio between the x tau, the value of the items that we picked, divided by the maximum xi, which is the value of the profit. Okay, so that's the competitive ratio, which is smaller than 1, and we want to make it as big as 1 as possible. So this, if we make some assumption that the one we're going to use later, the IID, if we assume that the x1, xn are, for instance, drawn IID from some distribution, we could solve this problem very easily doing some dynamic programming. Actually, it's not very easily. We can know the optimal strategy will be to do dynamic programming. But the issue with dynamic programming is that it's hard to compute usually, and it's almost impossible to analyze. So instead, what we're going to do is trying to look at for some simpler algorithm which has good property. Okay, and why should we do? Why is this interesting? Is because when you have like very simple algorithm, so typically an algorithm that depends only on one parameter, that we call it later like single threshold algorithm. So if you have just one parameter, when the data will follow some, when you will have access to some data with some unknown distribution, learning a single parameter is much easier than learning a very complicated dynamic programming. And so you at some point, you will have this trade-off between getting a very optimal but complicated algorithm, which is very brittle to the uncertainties that you have, and having very simple algorithms which are easier to learn somehow. So that's why we always keep in mind that we like simpler algorithm, because at some point it will be better in the future, in future works. So there's been a lot of recently lots of papers about those Profits inequality, essentially because as you can see, if you think of x1, xn as items, think of bids, for instance, you can say that okay, instead of running a very complicated auctions between different bidder, that's the bid x1, xn, I want to pick the highest one. I could just use a very simple algorithm that picks the very simple auction mechanism that achieve very good performance. And so that's why there has been a huge interest recently in profit inequality, because there is this trade-off between performance and simplicity in resource allocation. Okay, so that's the main idea. We see items sequentially. We pick one at some point. This is the value, and we want to be as high as possible, ideally as high as the prophet that knows everything in advance. Okay, so that's the main idea. And so as I said before, I will just during the first part of the talk, what I will do is I will cover somehow some of the literature so that you will understand the limits and the drawbacks of the existing approach, and then we will try to go beyond those limits. Okay, so let's look at this standard literature, standard results on secretary and profit inequality. So the simpler one is what we call the secretary problem. So the secretary problem, when you're doing a secretary problem, that's the oldest problem look in this online stopping time. So we have those random variable x1, xn, and those random variable has non-negative value, but with unknown distribution. Okay, and we have no idea what are the distribution. And in the subsequent, in the rest of the talk, I will get rid of this assumption. But here for this slide, assume that x1, xn have unknown distribution. It will be important for the future, for the open question at the end. Okay, so I have x1, xn, and what I want to do is I want to maximize the value of the item I pick, x tau. But since I have this distribution are unknown, it might be the case that x1, the maximum of the xi, is arbitrarily larger than the second max. Okay, so basically all the values depend on whether you pick the max or not. Okay, and so if you think that the maximum of the xi is very, very much higher than the second max, then the ratio between x tau and the max xi in expectation is just the probabilities that you pick the max. Okay, so in this secretary problem, the question becomes of can you define an algorithm that select the maximum xi, that selects the maximum item, the item with the maximum value with non-negligible probability. And so that's the main question. And the question is, can you create a non-trivial algorithm that select the maximum value item, even if you have no idea about the distribution of all the items? And the answer, of course, is no. There is no way of doing this because you cannot see the future. You have no idea of what's going to happen, so there is no way. And just the way to convince yourself, I'm not going to do the proof, but let's say that x1, the first value that you see is 1, and you have to decide whether you take it or not. If you take it, then maybe x2 is plus infinity, so basically the ratio is 0. And if you don't take it, it may be the case that x2 is 0, and so you get at most 0, and well, the prophet gets 1. So you have no way of getting a good ratio, a non-negligible ratio with a deterministic algorithm, but we can do the same type of proof with a random algorithm. Okay, so if we don't put more assumptions, there is no way of solving this problem of getting a picking rule that has non-negligible probability of picking the max. So what you want to do is you want to add some assumption, and the typical one is to assume that actually the x1, xn, the items, they are not observed in some specific order, but in random order. So basically, there is this permutation, this random permutation, call it sigma. And what you're going to see is you're going to see first x sigma 1, which is the first item drawn at random, and then the second item drawn at random from this pool of items. Okay, and in this case, it is possible to devise an algorithm which has non-negligible probability of picking the highest item. And this algorithm, there is a very simple type of algorithm which is very well known. Actually, it's sort of a magic trick because you have no idea what the xi are, but you have a way of picking the maximum xi with non-negligible probability. And there is a very simple way of saying, well, I'm going to see n items. What I'm going to do is I'm going to just discard the first n over 2. The first half, I just discard them, I just look at the value. And then I will just focus on the second half. And on the second half, what I'm going to do is I'm going to pick the first item whose value is higher than the max I've seen in the first half. Okay, so the first half you discard. Then you fix a threshold, which is the maximum value you observe in this first half, and then you pick any item in the second half, which has higher value than this threshold. And this gives a probability of winning of 1/4. Actually, it's more than 1/4. And the idea is very simple: is that if the second highest value is in the first half, and the highest value in the second half, you win. Okay, because the threshold that you fixed on the first half is the second highest max, and the only items that goes beyond this threshold is the max, and so you win. And so this happens with probability 1/2. The second max is in the first half with probability 1/2. The max in the second half is probability 1/2. So this happens with probability 1/4. But actually, yes.
There's a question in the chat just clarifying whether
Oh.
x1 through xn are IID in this case.
Right. No, they are not IID. They are nothing. We don't know anything about x1, xn in this case. They are not IID. Yeah. If they are IID, it's a bit more complicated. Okay, but just in this case, in this very simple case, secretary problem, they are not IID. Okay, so with this naive algorithm, I check my data in two. I learn on the first half, and then I apply this threshold on the second half. I get 1/4. And actually, this is not exactly 1/4 because sometimes the probability of winning is higher than 1/4 because I'm also winning if the third values in the first half and the second and the max are in the second half, but the max arrives before the second half. So it's slightly higher than 1/4. And actually, if I'm trying to make all those computations and I look at what is the optimal algorithm, the optimal algorithm is not doing 1/2, 1/2. It's doing exactly the same kind of technique. You're checking your data in two parts, but the first part is only n over e. On this part, you're learning the distribution, and then to fix a threshold, and then you pick any items with value higher than the max on the first discard items. So what I'm saying that you're learning the distribution is because with this random ordering, it happens that the x sigma I, those random variables here, x sigma I, they do have the same distribution. So they have the same distribution with uniformly over the set x1, xn. But the thing is that they are not identical. They are identically distributed, but not independent. Okay, they are correlated. Okay, so if you have data which has, in this case, which has same distribution, but some correlation, you can achieve 1 over e using this stupid algorithm. Okay, you just discard one of the first proportion 1/e, and then you fix the threshold. Okay. So then we move to the case where so we want to add more and more assumption to improve the performance of the algorithm. So now we're going to assume that those data x1, xn, they are still drawn from some distribution, but might be different. And the distribution, this time they are known. Okay, I know that x1 is drawn from f1, x2 from f2, and xn from fn. Okay, and here we ask the question whether it's possible to create a non-trivial algorithm that has a good competitive ratio, higher than 1/e, typically. So here there is the question is the maximum threshold you can achieve is we call the competitive ratio, the ratio between the performance of the algorithm and the performance of the prophet is smaller than 1/2. And the proof is just using this counterexample. You will take, well, here I forgot, but you take x1 as a typo. You take the following distribution. You assume that x1 is 1, always equal to 1. And x2 is equal to, is very large, huge. That's very important for us, actually. x2 is huge, probability 1/epsilon, with a very small probability, epsilon. And this is a typical counterexample, because if you take the maximum is going to be 1/epsilon with probability epsilon, and 1 with probability 1 minus epsilon. So the max of the xi is epsilon times 1/epsilon plus 1 minus epsilon. So it's the expectation of the max is roughly 2. And if you take any algorithm, the algorithm will either pick the first random variable or the second one. And any algorithm will have an expectation of 1. So no matter what you do in this case, you have a ratio of 1/2. So this means that the competitive ratio of an algorithm cannot be higher than 1/2. And it happens that there is an optimal algorithm, very simple algorithm, the single threshold, that is just one parameter. And this is the following, that the algorithm is just to take any xi which is greater than the median of the maximum of the xi. If you do that, you're guaranteed that in the worst case, no matter what the distribution of f1, fn is, you will get at least half of the expectation of the max. And something which is funny is that you can also take as a threshold the expectation of the max divided by 2. So either the median or the expectation of the max divided by 2, or of course, for some reason, because it's a concavity reason, any point in between. Okay, so that's in the secretary case, if you don't have any knowledge about distribution except random ordering, you get 1/e. If you go in IID, if you're in non-IID case, so you know distribution, but they are not IID, you get 1/2. And now the question is, what can happen if you go, again, you're adding some assumption and you assume that the data are IID. Okay, and this is what's going to be important for us. From now on, I'm going to assume that the data are IID. Okay, so I assume that the data are IID. So I have x1, xn, IID, drawn from some distribution f that I know. Okay, so I have ID data drawn from f I know. And I'm asking you the same question. Can I define an algorithm such as the competitive ratio, the expectation of x tau divided by the expectation of the max is as big as possible for any instance, for any distribution f. And here we're going to see how it works, because actually that's how I will base my algorithm later. I have this, if I stick myself to very simple algorithm, so single threshold algorithm. A single threshold algorithm is an algorithm that says you have one threshold, here I'll call it theta, and you pick any random variable which is higher than theta. And if you look at single threshold algorithm, there exists an algorithm, I will show you how, that achieve 1 minus 1/e. Okay, that's because it's IID. And this is roughly 0.63. So this is optimal. You can always find an instance. We'll see in a few slides that proves that you cannot get better than 1 minus 1/e, but you can achieve this 1 minus 1/e. And now if I'm allowing myself to look at more complicated algorithm, even if I go all the way to dynamic programming, so here we'll have like we call dynamic threshold. It means that I will accept xi as the ith random variable if and only if it's higher than theta I. We can show that this is optimal. There's no way of, I mean, if you accept some xi, you will at some point you should always accept it if it's higher than this value. Okay, that's always optimal algorithm. So if I'm looking at this dynamic programming, if I'm looking at the optimal algorithm, This is no, it's like a 40 years old result that shows that the optimal competitive ratio that you can achieve is roughly 3/4. Roughly, it's a bit less. Okay, it's 0.7455. And there is a bunch of numbers after. This is just an approximation. And 10 years ago, José Correa and his co-author proved that there is a simple algorithm that actually achieve this competitive ratio without going all the way to the dynamic programming complexity. So let me. So now what I'm going to do right now is I'm going to because I mean it's at least some maybe the most important part. I'm going to show you I'm going to give you some intuition about the proof of those two results, and then I will claim that, I mean, looking at this worst case analysis where I want something that holds for any f is not a good idea, and I should look at something weaker. But then the algorithm I will define will be strongly based on the typical proofs that I will show you in the next few slides. Okay, so the next few slides.
So Vianney, what is the objective? Is it mostly to come up with better analysis of these algorithms, or to discover like more general more powerful algorithms?
So the question is actually it's in between. Sometimes you can either claim, well, I want to have like a better. It could be both things. Say, well, I'm going to look at what I want to do at the end. He says, I want to look at nicer distribution f, and if those distributions are nicer, and it will depend what nice mean. In this case, I can find a better algorithm, okay, which are better in the sense that they achieve a higher competitive ratio, okay, because here the thing which is funny, which is surprising, is that the simple algorithm of Correa et al. That achieves this competitive ratio of 0.7455 always achieve it. Always, no matter the instance, it's designed to achieve this ratio of 3/4, no matter what the distribution are. Even if the distribution are very simple, and you could achieve more than this algorithm, which is optimal in the worst case, only focus on this 0.3/4. 3/4. And so the point is, say, well, if you allow yourself of saying, well, let's look at more of nicer distribution, I could find better algorithm in the sense that they will have a higher competitive ratio. Okay, they will have a higher competitive ratio on a restricted class of problem. So that's the whole point. And actually, so that's one direction. And the other direction, you say, well, actually, this competitive ratio is a bit too specific and pathological. And so we're going to look at a benchmark which is slightly weaker. And if you just look at something slightly weaker than this competitive ratio, you will improve a lot your performance somehow. Okay. Okay, so let's look at the proof of the single threshold algorithm. And you see the proof is not that difficult, okay? But it just makes this function here, R of Q. So I want to do this proof because it's very elegant. It's due to some of the idea are due to Rosé. And then there is another question in the chat. Okay, thanks. Okay, no, maybe I should do it like this. Okay. Okay, so R of Q, this function here, R of Q, what is it? It is just the value that you get when you reach an item. And if you decide to pick this item with probability Q, okay, so you fix the threshold so that you will pick this item with probability Q. So the threshold is the Q quantile of your distribution, okay? So that's what he says, this is the threshold here. So that's the Q quantile of this distribution. So you pick this item with probability Q. And so if you decide to pick this item with probability Q, what you will get is with probability Q, you will get the expectation of X, knowing that X is higher than the threshold. Okay? So this is just a quantity that says that the expected reward of accepting an item, if you fix the probability of picking it to be equal to Q. Okay, so it's just this. And this quantity it has the formula, an integral formula, which is just helpful to show you that R is concave. Okay, I just need this. And actually, something which is very important is that there's this formula here that says that the expected value of the maximum of the profit is just n, that number of items that you see, times the expectation of R of Q. where here the expectation is over Q, and Q, the law of Q is some beta distribution. Okay, so here you can just take it for granted. I mean, proving it is just analytic computation, just doing twice integration by part. It's not really important. Okay, but what's really important is that the prophet gets n times the expectation of R of Q, where Q has this law, this distribution. And R, you know, with this function, this is this function above. Okay, and so now what I'm going to do is I'm going to work everything on R, on this function R. And I want to build a single threshold algorithm. So this single threshold, I'm going to compute a threshold that corresponds to a quantile of 1 over n. Why? Because actually the expectation of Q, when Q is a beta 1 n minus 1, is 1 over n. Okay, that's why I'm picking it. So here it basically says that the first item, when I see it, I decide, before seeing it, I decide to pick this item with probability 1 over n. And if I don't pick it, I go to item 2, I will pick this second item with probability 1 over n, of course, if it's higher than the quantile, and so on and so forth. Okay? So then when I look at the expectation of my algorithm, each time I see a random variable, I get R of Q, because that's the probability of getting this item times the expectation of the value of this item. So each time I see a random variable, I get R of Q. And I will get how many times I will see this random variable, depending if the stopping time is higher than I. Okay, and of course, I will see the first variable I will see with probability 1. The second variable I will see with probability 1 with Q, because otherwise I will pick the other one. The third variable I will see with probability 1 with Q square, and so on and so forth. So this algorithm, when you have a single threshold, there is this exact formulation for it, is that it's R of Q times this sum here. And this sum, of course, is a geometric sum, so I can make the computation. And I can see that this is R of Q times this quantity, it's just doing standard computation. This guy here, because Q is 1 over n, is higher than this quantity here. So it's very simple math. And so I end up being in this case here. So my algorithm gets R of Q, small q, but Q is the expectation of the random variable Q. And since R is concave, by using ENSAE, I know that what my algorithm gets is higher than n, which is this guy here, times the expectation of R of Q, times 1 with 1 over E. And the first term here is exactly what the max gets. So in just one line, using the fact that R, this function R, is concave, and the ENSAE inequality, I can prove that picking the single threshold of 1 over n gets ensure the quantitative ratio of 1 minus 1 over E. So that's how you get the proof, using this formulation of R of Q. And then here again, I'm going to explain why it's optimal. And you can show that if you pick for F a very degenerate distribution, for X is a random variable, so we're going IID. X is going to be large, equals to n, with a very small probability, 1 over n square, and the constant, so here I put the constant to 1, actually it should be something smaller, but let's say it's 1, with probability almost 1. So if I take this distribution for X, I can show that the expectation of the max as before. So the max, you have n random variable, each one of them is equal to n with probability 1 over n square. So basically, the max is equal to n with probability 1 over n. Okay, so that's roughly the idea. So the max is equal to n with probability 1 over n, otherwise equal to 1. And so the expectation of the max is 2. And you can show that no matter what the algorithm you're doing, you cannot get, the algorithm gets at most 2 times 1 over E. And this proves that this instance, you have any single threshold algorithm gets at most 1 minus 1 over E of the max. Yes, Ali.
A question by Ali Reza in the chat. Does Q have a Bayesian interpretation? So the Bernoulli distribution, it reminded Ali Reza of the Bernoulli beta conjugate priors. So is there a non-analytic way of making sense of, I guess?
Yeah, I understand. Of getting this formula here. That's a good question. I never asked myself this question. It's a good question. Yeah. I don't know. That's a good question. Yeah.
Another thing that occurred to me was whether this, if you think of this as, if you think about the inverse CDF method of sampling a random variable, this feels like, oh, you're sampling your n uniforms, taking the maximum, and then plugging that into F inverse.
Yeah.
And then somewhere a factor of n happens, which I can't track in my head. But and there are connections between that and the Bayesian thing, but that is sort of not obvious. But I would guess that the inverse CDF is the easiest way to say it.
Yeah, maybe not right, because it's true that like there's this thing that says that when you have like all of those x1, xn, when you fix one random variable x1, this random variable, since they are IID, x1 is the max with probability 1 over n. So it makes sense to pick it with probability 1 over n.
Right.
And x2 is the max with probability 1 over n, so it makes sense to pick it with probability 1 over n. But the fact that there is an inequality, and here you can use this kind of proof like doing some stochastic dominance argument, and you can show that this is higher than something. But here, having the equality is more trickier, more tricky, and not 100% sure. But but that's a good question. Yeah. Okay, so let's move on. Unless there is another question. Okay, so on this distribution, it's not really important. I mean, to the detail. What's important here is that, trust me, this is the worst case distribution. So it's a counterexample, says you cannot beat the 1 with 1 over e. And here what's important is that this x is very large with a very small probability. Okay, very large with very small probability. So it's a degenerate. Okay, it's very degenerate. So of course you cannot get, thanks to this counterexample, it says that you cannot beat this 1 with 1 over e with a single threshold algorithm, but it's with a degenerate distribution. So now I'm going to give you the intuition about why we can, with dynamic threshold, we can achieve more than this and we can achieve 3/4. I'm going to just give you the intuition of the proof. Again, it's just a basic argument. And then it will be just going to say that my algorithm actually are more involved, but they rely on this argument. Okay, so here, the expectation of the max, it's still n times the expectation of RQ. This we know. And since Q is beta, so we have some density. And I can write this quantity as n times the integral of R against psi, where psi is the density of the beta. So now, if I'm using threshold, which are dynamic threshold, θ1, θ2 up to θn, that corresponds to quantile Q1, Q2 up to Qn. It's true that the expectation of my algorithm, x tau, is equal to R of Q1 plus 1 minus Q1 times R of Q2, and so on and so forth. Okay, so I know that the max is an integral, and my algorithm is a finite sum. And so the main idea of Rosé and our colleague says, well, what I want to do is I want to approximate the integral by this sum up to some multiplicative factor. And then I will mimic somehow the optimal algorithm using this approximation between integral and finite sum. So now if I'm picking the Q1, Q2, those thresholds, such that each of those terms here, 1 minus Q1 times 1 minus Q2 and so forth, is roughly speaking gamma, this will be a parameter, times Qi plus 1 minus Qi times psi. So what I'm enforcing doing this is I'm exactly replacing this integral by an Abel sum. Okay, and then I have pages of computation and to prove that the Abel sum is higher than the integral and so on and so forth. But that's exactly the idea. So if I'm doing this, I can show that when n, let's say that you're going at the limit when n goes to infinity, I can replace this integral by an Abel sum. I know that it will converge, and so I know that up to this parameter gamma here, we get the same thing. Okay, and this parameter gamma will be the ratio, the competitive ratio of my algorithm. And then the whole proof say, well, let's try to find the highest gamma possible, such that all of those inequality here holds, are true. And Q1 goes from 0 and Qn goes to 1. Okay, so I have this linear program, I'm solving it. And when n goes to infinity, that's the worst case, I can show that all of those gamma will be like an approximation, a discrete approximation of some ODE. And so I can look at those ODE, I can look at the solution of those ODE, and the solution of the ODE will give me the optimal value for gamma. And you can just compute everything, and you will see that gamma is 0.745. Okay, so that's the main idea. The main idea when you have dynamic threshold is to somehow trying to approximate this integral by discrete sum up to some multiplicative factor, and this multiplicative factor will be the competitive ratio. Okay, so that's the main idea. Okay, so I'm roughly half of the talk, which is perfect because that's where I want it to be. So this is where this is the standard state of the art results, the standard proof, standard arguments, standard courses, whatever you want on Prophet inequalities. And here what I claim is that at each time we say, well, we cannot improve those rates because you have like we have those distributions that are degenerate, and they show that we cannot get more than 1/2 or 1/1/e. Okay, and so here what I'm saying is that each of those worst case distributions are very degenerate. And actually, they are not even the distribution. Because if you think about the distribution, it was with probability 1/n² equal to n. So if you're looking at the limit, somehow the limit of this distribution is actually with probability 1 is equal to 1. And so if you're looking at the limit distribution is very easy. This Dirac mass is at 1. So the problem is is just at the limit. There's some weird stuff that happens at the limit because we look at the degenerate pathological distribution. And not all of those actually, if you're looking at some instance, a specific instance, they are not all difficult. Some of them are easy, some of them are not that difficult. Okay, so what we claim is that we should get rid of trying to beat the Prophet in all the instances and say maybe we should. So there is two ways of going above this worst case analysis that we study. The second one is to say, well, like if you have instances, if we could parameterize, give a measure of complexity of an instance, can I explain what is a difficult instance and what is a simple instance by some parameter, such that the competitive ratio, the ratio of an algorithm divided by the Prophet is high. If the instance is easy, it's higher. If the instance is difficult, it will be smaller. So something between 1 and 0.745. So can I do that? Or equivalently, can instead of looking at the value of the Prophet, can I look at some as a benchmark which is weaker? Okay, something slightly weaker than the expectation of the max. And maybe I will have a ratio which is much better if I'm looking at something weaker. Okay, so that's two ways of going beyond worst case analysis. Is saying, well, I don't want to look at the worst case Prophet, the worst case benchmark, or I don't want to look at the worst case distributions. Okay, so that's two directions. And like we had two papers, so essentially with Mathieu Molina, a PhD, one of a PhD with Patrick Loiseau. And we look at those two directions. Okay, so trying to get more precise results, saying, well, okay, so if we have degenerate distribution, we cannot be better than those proofs, okay, because we have upper and lower bound matching, upper and lower bound, okay. But if we look at non-degenerate random variable, what can we say? Okay, so that's the two directions that we look at. Okay, so the first one is very interesting, and I will say, okay, let's look at weaker benchmark. Okay, so what I call by weaker benchmark, I'm going to assume that I want to be good. So instead of comparing an algorithm against the value of the max xi, I will compare the value of an algorithm with the Prophet that has to pick whose performance is the average of the top L. Okay, you fix L, its parameter. So if L equals 1, you end up with the previous cases where you have the standard Prophet inequality. And if you look at, for instance, the top 2, so you say, well, I want to build an algorithm which is good against whose performance is higher, compare it to a prophet that has to pick the max and the second max divided by 2. Okay, that gets half of the max and the second max. Yes.
I mean, could this be could this be greater than 1 then?
It could be greater than 1. It's not, but it could be, yeah.
Okay. So exposed, it's not, so it's okay, but it could have been.
Well, it's not yet. It's not greater than 1 if you take the infimum over all the f. But it's true, it's correct that it might be the case. And then we see in a generalization where we're going to look at weaker version where the algorithm has to pick 2 items and we get the average value of them or the sum of the value. And the prophet also picks 2 items. Okay, so this is always smaller than 1. It's more fair in some sense. Because here what I'm saying is that it's a way of saying, well, I'm giving more power to the algorithm than to the prophet. Okay? Because the prophet has to make L choices, while the prophet can only make the algorithm can only make 1. Okay, so indeed it might be the case that the cooperative ratio is higher than 1, but it's not. Case by case, it might be, but not when you take the infimum. Okay, so when you have this problem, you can write something, and which is correct, but a very bad idea. Is say, well, like I want to control the ratio between the expectation of x tau and the average of the top L random variable. So what I can do is I can just squeeze in the expectation of x1 and write this ratio as the product of 2 ratios. Okay, those 2 ratios here, you can see here and here. And what's happening is that on the right here, you can see you have expectation of x2 divided by x1. So it looks, because it's important, like the usual competitive ratio. And on the part on the left, you have another ratio. And so this infimum over f of those 2 products, you could say that this is greater than the product of the infimum over the infimum of the 2 ratio. But here, the ratio on the right is 0.745. We've shown it before for some f prime, which is degenerate. And the ratio on the left, the infimum, is 1, but for a completely different degenerate distribution. So here, of course, when I take the infimum of those 2 terms, I will still get the 0.745 that I had before. But to do that, I need to take for one ratio a degenerate distribution, and for another ratio another degenerate assumption, and they are not the same. So the infimum over the product is not the same as the product of the infimum. And actually, they are far away from being equal, and they are very far away. And what we can prove actually is if using the algorithm, I will show you later, but it's just 1 line, is that if you're looking at our algorithm, which is a variant of the algorithm of Jose Correa, as I mentioned before, when you try to mimic the integral, you can show that you have some closed form, more or less closed form expression for the competitive ratio, which is the solution of this thing here, which is a total nightmare, I agree, because it's like it's not very easy to pass. But if you make the computation, you can see that if you're comparing your algorithm against the top 1, the max, you get this standard 0.745. But as soon as you compare your algorithm to the top 2, the average of the top 2 values, you jump from 3/4 to almost 1. And then if you compare you can see that those numbers, which is the ratio, increase incredibly fast to 1. Okay, and if you compare your algorithm, say, well, okay, reaching the max value is too difficult because I have those degenerate distribution. But if I compare against the top 5, the average 5 or the 5th, which is the same, the 5th value of my distribution, I get a ratio which is 0.9999993. Okay, and as you can see, you can prove that actually it goes exponentially fast to 1. So here the message is competing against the top value, the max value, is too difficult because you end up having like degenerate distribution as we have seen before, one which is actually you end up having distribution which are very large with a very small probability, and you cannot foresee it in the future. But as soon as you say, well, I'm fine with competing against the second max and not the max, but the second max, then you get a competitive ratio with respect to the second max of 0.966. Okay, so the whole difficulty of Prophet inequality, which was you achieve a quantitative ratio of 3/4, is because you only look at degenerate distribution. Degenerate benchmark. Okay, you have a benchmark that induces that degenerate distribution are too hard to achieve. It's too hard to find the max because it's arbitrarily high with a arbitrarily small probability. Okay. The algorithm that I just said is exactly the same thing as the previous one that we see. You can show that the expectation of opt, as we've seen before, what opt gets is still n times the expression of RQ, but where Q is no longer a beta 1 n minus 1, but actually it's a beta L n minus L. And so you can do the same ID, except that you need way more pages of technicalities to make sure that everything works. But the ID is the same. Okay, you have like this integral that you're trying to mimic to approximate by a discrete sum using the same kind of ID, but it's a nightmare. Okay, it's a nightmare to get it. Okay. But see, what I'm saying is that you can see that, or maybe I should get to the next one. So now if I'm looking at the case where I'm forcing my algorithm to pick not just one, but k items. So, okay, so here it's on each line is saying, well, I want the algorithm to pick one item or two item or three item or four item or five item. And I compare the average value of those k items and the prophet gets L items. I'm looking at the average value of the items, and then I look at the ratio of performance. I can see how those things evolve with time. I have a formula, so I can make all those computations. And as I said before, of course, as soon as L increase, so I'm increasing the power of the algorithm. This competitive ratio increase incredibly fast, and when K increase, it's when I decrease the power of my algorithm. The competitive ratio decrease very fast. Yes.
Two quick questions. So how do you define the benchmark with K? And my second question is, this seems very powerful, but in some sense it begs like the question, what is the right benchmark? Because this is also like a benchmark that maybe is not micro-founded in some sense. Like it's not clear why I should be looking at the average top. So like, can we kind of come up with like an ideal benchmark to compare to with some sort of micro justification?
So yeah, so did I write? No, I didn't write. So if you have k items, you pick k items, you look at the ratio between the average value of the k items that you picked divided by the average value of the top L. Okay, it's quite natural. And take the minimum over all distribution. Okay. So now the second question is actually independent of k, but it's true. The second question is what is the what would be the natural benchmark? And actually, so in this case, in many instances, actually, finding the optimal algorithm is not that difficult. Okay, because you know that the optimal algorithm, if you know all the distribution, is you can do it by dynamic programming. Okay, if you can compute it. So let's say you can compute the dynamic programming, and so here it's more like what is the cost of not knowing the future in advance versus and so if you know that if you have an algorithm that achieves this competitive ratio, of course the dynamic programming, which is optimal, will get more than this. So I think it's not clear. The optimal algorithm is always dynamic programming. That's what I want to say. It's always dynamic programming. And so yeah, so it's not clear. It's not. So here the message is more like if you focus, it's more like the fact that when you go from the max to the second max, so you're removing some degeneracy, and the problem becomes much simpler. So here the message is more like the 3/4 that we will see, the 0.7455 that we all know about when doing Prophet inequalities, is due to the degeneracy of the class of distribution that you're looking at. Okay, because you're looking at And so when you're looking at the second max, actually, those degenerate functions, they disappear because like the one that we've seen before, which was equal to n with probability 1 over n squared, the second max is 1. Okay, so you get the max n, but you also get the 1. Okay, so actually the value of the average is no longer n, but it's n over 2. And if you look at the value of the second max, it's not n, but 1. So it's a way of saying like we should get all the difficult part of it is because there is those degenerate distribution, and we should not focus too much on them. Okay, that's how I interpret this kind of results.
Thanks.
And actually, that's exactly because here, I'm almost out of my time, so just like a few minutes, but this already, I'm just need 5 minutes. So this is exactly what we did in this paper that we call beyond worst case with analysis with variational analysis. And so what we were saying is that, so we had those results saying that we cannot beat the 1/1 over E. If you're looking at a single threshold algorithm for IID random variable, we have seen that the optimal threshold is 1 over n for all the random variable, and this gives you 1/1 over E, and you cannot beat it. But this is only true if you're looking at worst case instance. If you're looking at very simple instance, think of like if I have Dirac masses, all the random variables are equal to 1. By picking any of them, I get a 1. So if I have a very difficult instance, I get a competitive ratio of 1/1 over E. This we know. And if we have a trivial instance, we can go all the way to 1. And the question that we're asking is, can I measure somehow the complexity of a distribution such that so I have a measure of the complexity such that the competitive ratio, the ratio of performance given this complexity will be between 1/1 over E and 1. And can I interpolate smoothly between 1 and 1/1 over E when the complexity increases? And so that was the point. Say, well, let's get rid of the degenerate distribution and focus on simple distribution. So now what simple distribution means could be, well, I want to look at xi, which are bounded, but this makes no sense because the competitive ratio is scale invariant. So it cannot be the bounded. It cannot be the variance itself because the counterexample has bounded variance. So it has to be something more. And actually, what is really important is not just the distribution of a random variable, but the distribution of the max. Because the horizon is very important when you're doing online decision making. And so what we understood is that the very good complexity measure is actually looking at the variance of the max normalized. And so here I'm normalized by the expectation of the max square. So it's just normalization so that it's you can think of it to be 1 if you want. So it's the variance of the max normalized so that we get rid of this multiplicative factor. And why is that? Because if the variance of the max, or the 2 should be up here, is 0, it means that the xi are deterministic. And so the problem is easy. And if this variance is very large, then the xi are EV-tailed. And so the problem are difficult. And actually, when you're looking at some example, it is the case that for uniform distribution, the variance goes to 0, the competitive ratio goes to 1 when n goes to infinity. For exponential, it's the same. For the Pareto distribution, you have the variance of the max is constant, and the competitive ratio is a constant. And for the worst case, we take like very complicated random variable, the variance of the max is plus infinity, and the competitive ratio goes to 1/1 over E. So here, intuitively, we can interpolate between 1 and 1/1 over E, depending on the complexity of the instance. And it happens that this is exactly what we can prove. We can prove that with some closed forms. So it's not closed because it's a solution of this weird max-min problem. So this comes from variational inequalities. So we're sparing you the detail. But it is true that if I'm focusing on all distribution f and horizon n such that the variance of the max is smaller than gamma, so this is the parameter I fix, I'm looking at non-degenerate function, non-degenerate being that the variance of the max is smaller than gamma, then the competitive ratio is over this class of function is the solution of this problem here. And I'm sparing you the detail, but then you can get this curve that shows that the more complex the instance is, so the higher the gamma, the smaller the competitive ratio. And of course, it interpolates between 1. That's when gamma is 0, it's when you have like deterministic random variable. That's very easy. and then it drops all the way to 1 over E when the instances are very difficult. Okay, so this parameter gamma here that it's the variance of the max, which makes sense actually when you think about it. I mean, when you see it, it's obvious that this correct answer is a good parameter that says, well, this parameter controls the complexity of the problem. And so I'm skipping the proof. And I'm just going to do like doing the open problem because I know it's written somewhere that we want to see open problem. And so I'm just going to tell you, if you're interested, if someone is still here and still following, what would be the good open problem, very interesting open problem, I'm sure actually what it is that what happens if you have x1, xn, which are IID, and f is unknown. You don't know f. So there are negative results that tell you that this is impossible. You cannot do it. You cannot learn. There is no way of doing it. But always, there's no way of getting a complexity ratio higher than 1/3. But that's correct, of course. But the argument always involves some degenerate distribution, which has no moment. Okay, so you cannot learn, of course, because you have no moment. So you cannot learn anything. And so the question that I'm asking is, what happens if you say, well, let's get rid of the degenerate distribution, because it makes no sense of trying to learning a degenerate distribution. So let's get rid of the degenerate distribution, focus on low complexity distribution, and what can you do in low complexity distribution? Can you learn the optimal a good algorithm in for low complexity distribution in the IID case? So we have some work where we're trying to do it, but in some specific case, but it's still very open. And yeah, I will just leave you on those takeaways, which are the main message. And so if you have any question, I'm less than happy to answer it.
Thank you very much, Vianney. So are there any questions in the chat? So I guess like on the open question, which is I think a question that interests quite a few people in the room probably, whether the negative result here, how is it? Is that like a known result from the literature, or is this something
Yes,
that
it's a known result.
an adaptation from the?
Yeah, there's a bunch of paper by Duting, notably, and his co-author, and many other people. I forgot. This is maybe I should I haven't said just one name because it's like a bunch of them. And what they prove is actually if you don't have prior knowledge, extra sample from those distribution, you cannot do anything. And you cannot do because again, because there is this result, which is a very nice result by I forgot her last name. So it's Rebecca. Anyway, so sorry about I'm very bad. I'm remembering names, so it's awful. So if you have x1, xn, so if you get just one sample from each of the distribution of x1 up to xn, with just one sample, you can create a threshold, which is the max of the fake sample that you have seen, and this achieves the complexity ratio of 1/2. And this is another open question. So if you have actually, it means that if you have one sample of the max value, you can achieve a complexity ratio of 1/2 with just one sample. But so the counter example here, where you have negative results, is because you still need this kind of thing, and if you don't have it beforehand, anything, yeah. And if you don't have it, you can say, well, I'm gonna try to spend half of my budget trying to learn the optimal threshold as we did before. But if you don't this, it's already too late because you already implemented the secretary problem. Yeah. Basically, so if you don't know f, there is no way of beating this 1/E because you can have like a very weird distribution. Okay, that's why you need to make some assumption. And the one that makes sense will be, I guess, it will be to say, well, okay, I'm going to assume that the variance of the max is bounded by this quantity. Maybe you know it or you don't know it. And maybe you can just guess it and say, well, I guess the max is smaller than this. If I'm right, then my predictive ratio is small, is higher than, I don't know, like 1/E. But if I'm wrong, then I have a complete ratio which is goes to 1/E or something like this. But I mean, there is a way. There is a way of going. So those results are correct, but there is a way of saying, well, they are too broad somehow. If you restrict your attention to the smaller class of description which are learnable, then you should be able to learn them. There was a question, I think, in the chat at some point. I saw it, but I don't know if it's maybe it's an old one. I don't know. No. Yeah. So
I think it was a previous question.
Okay.
Yeah.
So what I'm saying here is that those pathological counterexample actually also happens in standard if doing machine learning, and I'm giving you data that has no moment, you cannot do anything. Okay, and that is the kind of result that they prove that if you have data which are very degenerate, where you cannot do learning, then you cannot do learning, which is somehow expected. But I guess
So what is 1 plus epsilon moment? What does 1 plus epsilon moment mean here?
it means that the expectation of x to the 1 plus epsilon is
okay.
is infinity.
I see.
So it's not exactly true, because always looking at, so what I'm saying that for every n, okay, so for every n, you have a distribution such that the competitive ratio will be like, I'm going to say something like 1/E plus 1/n, okay? And so what I'm saying is I'm looking at the limits. So I'm taking the limit distribution when n goes to infinity. The distribution is something very pathological, where they have it's a distribution which has no moment, absolutely no moment, just the first one, but otherwise at no moment.
That makes sense.
Yeah.